Okay, AP Chemistry students, good morning. We're going to be talking today about two things, Lewis structures for polyatomics, and we'll also be talking about formal charge, which can be used to determine the best structure for a polyatomic. So let's get into the polyatomics first off, and we're being asked to draw a Lewis structure for polyatomics, which follows a lot of the same rules as we did for just Lewis structures of any regular neutral type molecule. And so we have BrO3 1 minus that we're going to start off with, and so what I'm going to start off doing is I'm going to calculate the total number of valence electrons in this molecule. So for the bromine, obviously we have valence electrons of 7. We have 3 oxygens. They're going to have 3 times the valence number of 6. And we also have to remember, and this is one I always forget, and sometimes students do as well, is there's a -1 charge here, and that -1 means we've gained 1 electron, so we're going to add 1 more electron in there. So we have 7 plus 3 times 6, 3 times 6, 18, 19, so we got 26 total valence electrons to deal with here. We're going to follow the other rules here for drawing a Lewis structure. So bromine is going to be our central atom with oxygens, and I'm going to put them like this all the way around. And we want to once again make an octet onto everybody. So we're going to single bond first, single bond, single bond, single bond. So that uses up 6 of these valence electrons. So now I'm only down to 20. And so I'm going to go ahead and make my dots all the way around. So we've got 20. So we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, so we used up everything. Double check everybody. So this oxygen that I'm looking at right here with the arrow, it has 2, 4, 6, 8 valence electrons, so it has an octet, so we're good with that. Looking at the bromine in the middle, it's got 2, 4, 6 of the bonds and an unshared pair of electrons, so it's got 8. So everybody's good. So the last thing I need to do is the way we show that this is a polyatomic is we're going to put this whole guy in brackets like this. And then on the outside, we're going to put its charge. Its charge was a 1 minus. So we have to put those brackets in the 1 minus, and that shows this is a Lewis structure for a polyatomic. I'm going to scroll down here, and we're going to talk about phosphate next. And of course, we all know our polyatomics. So phosphate is the polyatomic of PO4 3 minus. And so again, first thing we want to do is we want to calculate the number of valence electrons we're working with. Phosphorus has 5 valence electrons. We're going to add in the valence electrons for oxygen, which 6, and we have 4, multiply that by 4 because we have 4 oxygens, and we're also going to add in, again, that 3 more electrons from the -3 charge. So 6 times 4 is 24, plus 5 plus 3, so we should come up with 32. Total number of valence electrons is 32. And this phosphorus is going to be our central atom here. So phosphorus, we'll put oxygens all the way around like this. And single bond everybody so far. There we go. Oxygens do not have an octet, but the phosphorus does. We've used up 8, so but 26 more to go. So let's go here. So we'll just go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's 24 there. My math was off a little bit. 24, 24, 26, 28, 30, 32. So okay, we have 32. Everybody's good now. And so again, finish this guy off. We're going to put everybody in brackets and put that 3 minus charge. And so that's how we do a Lewis structure for a phosphate polyatomic. Now, let's scroll down here a little bit and make sure we get these rules down here. So let's talk about these real quickly, and because we're going to apply these. We have this idea called formal charge, and formal charge can be defined as, or it's used as, to determine the most probable structure of a molecule if there's multiple ways to draw the molecule, and we're going to find out that there are multiple ways to draw a molecule. So we use formal charge to predict these multiple ways. And now we're going to do some calculations of formal charge on a Lewis structure, and so this is how we do the calculations, and then we apply these rules to this. So first off, it says all unshared or non-bonded electrons are assigned to the atom which they are found. Okay, so what that means is we just count the non-shared electrons. So let's say if we were looking at an ammonia molecule. and there was an unshared pair of electrons on the ammonia right there, we would say that those 2 electrons are now going to be assigned to nitrogen. So that's all that means. Okay, we count them. Okay. The next one. For any bond, a single, double, or triple, half the bonding electrons are assigned to each atom in the bond. So what this means is, I'm going to go back to this ammonia example here. If we were going to count bonds, so this ammonia in the nitrogen in the central atom on the nitrogen here, there's our nitrogen, we would count 1 electron from each single bond. So we would apply 3, it has 3 electrons assigned to the nitrogen plus the 2 unshared, if that makes sense. I'll give you another example of this. Let's say we're dealing with carbon dioxide, and here's what a structure of carbon dioxide would look like. And we're applying these 2 rules to, let's say, the central carbon. So in this case, the central carbon does not have any unshared pairs of electrons, so it's a 0. And then we would add in half the bonding electrons, so we have 2, 4, 6, 8 bonding electrons from each double bond, so half of it's 4. So we would add in 4, so we would assign 4 to that carbon. And sometimes we write them up top like that. Okay, and that's what we're talking about here. Now, continuing on, formal charge. The way we calculate formal charge is going to be the number of valence electrons on the atom minus the number of electrons assigned to the atom using the above rules. Okay, so let's go back to that ammonia example here, and say we're going to calculate the formal charge on this. Mess that up here. Let me erase that. Let's go back to this example here on that central nitrogen. So what we would say is, first off, we calculated above 5 for that central nitrogen. It had 2 unshared pairs of electrons, plus we added in half the bonds, so 3 electrons in each single bond, or each single bond counted for 1, and there was 3, so we had a total of 5. Okay, so now what we're going to do is we want to calculate formal charge on that nitrogen, so we're going to say the valence electron. So nitrogen has 5 valence electrons, and we're going to subtract from it the formal charge that we just calculated, which was 5, so we would say 0. So we would assign formal charge of 0 on that nitrogen. That's how that works. Okay. In general, the sum of the formal charges should be 0 on a neutral atom. Okay, so if we go through and calculate the formal charge for hydrogen on each one of these guys, we could do that easily. And then we added up each hydrogen plus the formal charge on the nitrogen, it would be equal 0. Or it should be equal to the charge on a molecule with a charge, which is going to be a polyatomic. Or the negative charge should reside on the most electronegative atom. Okay, so let's do some of these, and I think it'll become real clear once we do a few of them what we're talking about here. So let's deal with, first off, the cyanide ion, CN1-. So CN1-, we have to draw the Lewis structure for this guy first. And so central, well, we only have 2 atoms, so we have a carbon and a nitrogen. Carbon has 4 valence electrons, nitrogen's 5, and we have the 1-, so we're adding in 1, so we have a total of 10 electrons to deal with, single bond. I'm thinking there's going to be a triple bond in this guy, so 2, 4, 6, and that's how we get it there, 1-. Okay, so everybody's got an octet now. Carbon's got an octet, nitrogen's got an octet. Okay, so let's start off looking at this carbon, and we'll figure out what our formal charge for the carbon is. So, looking at this carbon, we have 2 unshared electrons. Okay, so that's a 2, and we're going to add in. We have 3 bonds. That would be 6 total electrons, but you can only take half, so that's going to be 5, just like that. So, right. Now what we do is we're gonna take the number of valence electrons on carbon, which carbon has 4 valence electrons, and we're going to subtract this value that we just assigned to it, 5, and we get -1. And so that means that the formal charge of carbon in this molecule is -1. Okay, let's do it now for the nitrogen atom. So here's the nitrogen, And what we're going to do is nitrogen has 2 unshared pairs of electrons. We're going to add in, there's 6 electrons in this bond, and so we only take half, so that's 3. And so we get 5. And then what we're going to do is we take the number of valence electrons.
Attention all social studies teachers, please report to B9. Your training is starting. All social.
Sorry about that. I guess all social studies teachers are going to B9. All right, so where were we? Okay, we were back at nitrogen here. And so what we're going to do is we have the number of valence electrons for nitrogen, which is 5. It's in column 5. And we're going to subtract out this number 5, and so we get a 0. So we say the formal charge on the nitrogen is a 0. So how to double check this? We're going to add the sum of -1 plus 0, and we get it equal to the charge. So this is probably the most likely formula, and we can live with that. Let me show you one more here, and then that'll be it for today, and there'll be some practice problems. Now, there are 3 possible structures for this thiocyanide ion NCS1-. And so let's talk about those 3 possible structures and use formal charge to predict which one of those structures is correct. So structure number 1 we're going to look at here is we could draw this molecule this way. That is a possible way to draw this molecule. It fulfills the octet rule. Everybody's happy. Everything's good. The next possible structure I'm going to draw down here, we can draw this guy with double bonds on everybody. And we'll do an unshared pair of electrons on the 2 opposite ends. And that fulfills an octet for everybody. And we can also flip it around, and we can go triple bond onto the nitrogen. And that fulfills an octet on everybody as well. So in this case, what we're going to do is we would use formal charge to predict who or which one of these structures is the most probable structure. And so let's do that really quickly here and see what's happening here. So I'm going to start off here up on number 1 with the nitrogen. And nitrogen has, as we see, 6 unshared electrons plus 1 electron in the bond, and that gives us a total of 7. And then it's got 5 valence electrons. We're going to subtract out 7 that was assigned, and we get a -2. So this is going to be -2 here. For this carbon, we have 0 unshared pairs plus 4 electrons in the bond, so that's 4. And then we have 4 valence electrons minus 4 assigned. That gives us 0. Let's put a 0 there. And the last one is going to be the sulfur here. We have 2 unshared pairs of electrons on the sulfur. We have 3 electrons from the bonds. That gives us 5. Sulfur's in column 6, so 6 valence electrons minus the assigned. And so we get a +1 there, so it's going to be a +1 just like that. Okay. So that -2 plus 0 is -2 plus 1 is -1. So that does equal -1. So we'll see how that goes, and we'll go down here to the next one. And so in the next one, we're going to do, we have 4 unshared pairs of electrons, 4 unshared electrons, I should say. I'm sorry about that. Plus, we're going to add in 2 electrons from the bonds, and that gives us 6. Nitrogen is valence electrons 5. Minus 6 equals -1. There for this one. For the carbon, we have 0 unshared pairs of electrons plus 4 electrons in the bonds gives us 4. Carbon has 4 valence electrons minus the sign number 4. We get a 0 there. And then on the last one, on the sulfur here, we have 4. We're going to minus 2, and that's going to give us 2. And then we're going to have 6. I'm sorry, I made a mistake there. This should be a plus. That's a 6. And then we're going to do 6 minus 6 equals 0. And so that's going to be a 0. So looking at the formal charges here, we have -1, 0, and 0, and they're going to add up to -1. Wait a minute. Okay, we had the same thing up here, -1 as well. Let's see what happens in the last one here. Okay, on this nitrogen, I believe I forgot to draw an unshared pair of electrons on this guy here. There should be an unshared pair there. So now we're all set. Everybody's got an octet, and so we're going to go 2 unshared pair of electrons plus 3 equals 5. And those are the 3 electrons from the bonds. Nitrogen has a valence electrons of 5. Minus 5 gives us a formal charge of 0 on the nitrogen. Carbon, again, 0 plus 4. 4 minus 4 equals 0. Kind of going fast now. And then sulfur has 6 unshared electrons minus, plus 1. 1 electron from that bond, that gives us 7. And sulfur is 6 minus 7 equals -1 and -1. Okay, and so we add those up. 0 plus 0 plus -1 equals -1 from the charge, and so we have -1. Okay, so everybody has a -1, so that does not really help us. But we have another rule that we apply, and so let's kind of scroll back up here to our rule, and that'll help us figure out what's going on. So it says up here in number 2, in general, the sum of formal charges should be 0 on a neutral atom or equal to the charge in a molecule. Well, in this case, the charge was -1 in every single one of our 3 possibles, so we go to the next thing and we say the negative charge should reside on the most electronegative atom. Okay, so that's what we're looking for. Who is the most electronegative atom here? And if you remember from general chemistry, our periodic trend on the periodic table, as we go down the periodic table, electronegativity decreases. And as we go to the right across the periodic table, it increases to the halogen group. And so on the periodic table, we have, let's see, we have carbon, which is here, we have nitrogen, which is there, and then we have sulfur, which is kind of like right there, and that doesn't really give us our halogen group. So we would say as we go to the right, nitrogen is more electronegative than carbon, okay? And then as we go down, it decreases, but nitrogen and sulfur are on a diagonal, and that makes things tricky. So I'm going to look up the values. So if I go to page 312 in the textbook, and that's in the white textbook, it might be slightly different in the blue textbook, we look up the electronegativity values. And for nitrogen, the electronegativity value is 3.0, and that's in a scale called Pauling's. And in the sulfur is 2.5. So that means nitrogen is the greater electronegativity. Okay, so if nitrogen is the greater electronegativity, that would let us know that whoever's the negative charge should be on the nitrogen. And so its most likely structure is going to be number 2, because the negative charge resides right there on the most electronegative atom. So that's how we decide if we have multiple structures. Okay, so that's today's lesson on polyatomics plus formal charge. There will be problems that are going to go along with this. They're going to be written up on the board. Hope you guys have a great day. Any problems that aren't finished in class will be homework.